So the last topic is using dimensionality reduction for achieving a sparse model. So you may remember principal component analysis and singular value decomposition from APS 1070. So the idea here is that we use some linear combination of the features and use those as predictors. So, and there are different ways that we can find these linear combinations. So today we're going to talk about PCR without nasal swabs and PLS. These are methods for finding those linear combinations. So the idea here is that the problem from the beginning was that P was large, so we don't want a model with P predictors. Instead, we want a model with M predictors. Or let me use capital M. Let's say we want a model with M predictors, where M is smaller than P. So for these M predictors, we need M linear combination of the features. So we have Z sub M as a linear combination of predictors is going to be sum of, let's say, some coefficient M sub J times Xj from 1 to P, right? So for example, if we have a data set with credit card limits, credit rating, whether someone is a student or not, income, and a bunch of other variables, we're going to take a linear combination of them and call it Z sub M. And we're going to use capital M such linear combinations. Therefore, our data, which maybe starts, like this, a data set like this, we reduce the dimensionality by using a data set where there are M columns instead of P columns. So this is dimensionality reduction. One method for dimensionality reduction is principal component analysis, where each of these new columns is what we call a principal component, right? And that gives us principal component regression. But before discussing PCR, in here, essentially, we get these linear combinations, and then we fit a multivariate regression on Z1 all the way to Z sub capital M using ordinary least squares. So in here, instead of changing the way we fit the model, we change the data and use the old traditional model that we learned from lecture 2. So now if you rewrite it, essentially this is going to give us some y hat. For observation I, it's going to have some intercept plus some theta j times some theta m times z sub m I m. So from m from 1 to capital M, right? So this is just what we get from ordinary least squares on these new transformations of the variables. And we can rewrite this and then see that essentially our predictions are still a linear combination of the very original features, x1 all the way to xp, except that their coefficients need to take some special form. So this is same as some sort of restricted model with what we are familiar with, beta j times xj from 1 to p, where these beta values, where beta j takes some special form, theta m times phi mj from 1 to m. So we can kind of reverse engineer this kind of dimensionality reduction. So we reverse engineer it and see that the function we get in here is also a function of the very original data that we had. So y hat is some intercept plus some coefficient times original features, as long as the coefficients in here take this restricted form. This is some very specific form that the effect size of predictor j in the original data comes from the weights that we use in here to kind of break it down into, let's say, different linear combinations, and the weights that those linear combinations received in that OLS fit on reduced data. So theta in here and phi in here together, they define the effect sizes of the original parameters. So in this sense, we are again using some multivariate regression function, which is a function of our original features. So this is just a general idea of using dimensionality reduction for getting a sparse model. And the way that we kind of operationalize this part, there are two possibilities. For finding these linear combinations, we can use principal component analysis and use principal components as as the new features. And then when we run OLS on principal components, that whole process is called PCR. The alternative is partial least squares. So first, let's talk about PCR. So with PCR in here, we use principal component analysis for reducing the dimensionality. So just a refresher on, oh, we don't have that much time. So just a refresher on principal component analysis. If our data looks like this for x1 and x2, if this is the scatter plot of two of the features, this direction is principal component 1. This is where the data has highest variance. And this direction, which is orthogonal to it, is principal component 2. And now when we use these new axes, essentially our data becomes, something with something like this. This is if we just rotate the data. But if we use principal component to reduce the dimensions, we can change two-dimensional data in here into one-dimensional data where we only have one axis, which is PC1. And in PC1, instead of these points, we just look at the images of those points on the line. So we change the two-dimensional data into one-dimensional data. So we converted a data set with 2 columns into a data set with 1 column. And now we can use PC1 with ordinary squares to get a regression function. And this is what we get here. On the x-axis, I have number of components. So if I just use PC1, I get a univariate regression model with only PC1. And if I kind of reverse engineer the process to find these values of the effect size for the original coefficients, they will be in here. So there will be, one coefficient. And this is essentially giving us a model with a sparse model. So this is a sparse model in the sense that it only uses one principal component. And then if we increase the number of principal components to 2, 3, all the way to p, which is 11 for the credit data set, we get something like this. You can see that similar to the case of ridge regression, they kind of appear gradually, but as we increase the number of components. So here the lower sparsity region is to the right and high sparsity is to the left. And then this one is just equal to ordinary squares on the original data. If we have 11 columns, do principal component analysis and keep all 11 principal components, it is as if we have not done any dimensionality reduction. So we just get the very same ordinary squares. So this is idea of PCR, and eventually its performance is usually not as good as ridge and lasso. So it's just an idea for combining dimensionality reduction with sparsity. One reason why this idea doesn't work is that here we're making the assumption that finding an axis where the data changes, where the features change, is informative for prediction. Well, this is not necessarily the case. Here we're finding these axes in some sort of an unsupervised way because there's no use of y in here. There's no reason to believe that this new axis that we have found has relevance for prediction, for predicting the response y. So in this sense, PCR uses some sort of unsupervised dimensionality reduction, and then PLS is meant to do some sort of supervised dimensionality reduction. So what PLS does is, in this part where it tries to find these axes, it also takes y into account. And that's why it is expected that we get better result from this. But eventually, in practice, PLS doesn't give us better, more accurate predictions either. So among the topics we discussed today, ridge regression and lasso regression are probably the main methods for getting a sparse model. After that, we have model selection. And then at the very end, there are these two ideas, which are not that common for data science. So in PLS, just to explain you a bit how we're doing this supervision, what we're going to do with PLS, sorry, we're going a bit over time. So with PLS, what we're doing is first, we fit P univariate regressions, right? So we have P predictors, we fit P univariate regressions, and kind of use the coefficients from those univariate regressions to build those ZMs. So with PLS, this is the formula for ZM. So for example, for Z1, it's going to be something like this, where this comes from these univariate regressions. In this sense, it is kind of a supervised way of reducing the dimensions. But as I said, in the end, PLS and PCR usually do not outperform the other methods. So ridge regression and lasso regression are the go-to methods. So thanks a lot for your attention, and see you next week.